Today we'll be looking at soil description and classification, soil grading and particle size distribution curves and how they assist us in classifying and describing soils. There is a wide range of particle sizes in the soil spectrum. At the top end we have the boulders, which are particles or grains greater than 300 millimeters, the size of a soccer ball or football. Next, the cobbles, between 150 and 200 millimeters. Less than that we have the gravels, ranging between 75 millimeters and 4 millimeters, with the coarse gravels and the fine gravels. Between 4 millimeters and 0.075 millimeters or 75 microns we have the sands, starting with the coarse sands, then the medium sands and the fine sands. Anything finer than 75 microns or 0.075 millimeters is considered to be a fine grain material. Anything larger than 75 micron or 0.075 millimeters is considered to be a coarse grain material. Note that the fine sand is considered to be coarse grain material because even though it's fine, as far as the sand spectrum is concerned, in the whole soil population it is considered to be a coarse grain material, because in each case 75 micron is the determining factor between fine grained and coarse grained. Particles or soil grains finer than 75 microns are considered to be fine grained, starting with the silts with the symbol M and the clays with the symbol C. Clays are finer than silts with particle sizes approximately 2 microns. In the fine grained spectrum we also have the organics with symbol O. Organics are fine grained materials that consist of decayed matter or have decayed matter present. To determine whether material is fine grained or coarse grained, we have what we call a 75 micron sieve. This sieve has very fine holes or very fine apertures, approximately those of hosiery or women's stockings. So any particle that's trapped by this sieve is considered to be coarse grained. Any particle that can pass through this sieve is considered to be fine grained. Here we have a sample of quarry crushed rock, which comprises of a range of particle sizes from the coarse to the fine gravels, coarse sands, medium sands, fine sands and possibly some silts and clays. In order to determine whether this sample is coarse or fine grained, we pass this material through a series of sieves, and if more than half the mass is caught by the 75 micron or larger sieve, in other words if more than half of the mass is greater than 75 micron, the soil sample as a whole is considered to be coarse grained. If more than half of the mass of the total sample passes through all the sieves, including the 75 micron sieve, and is caught by the bottom pan, then the material is considered to be fine grained. Sieves range in a variety of sizes, and before we conduct a mechanical analysis we first need to remove the particles greater than 63 millimeters, and to do that we'll need a sieve with 63 millimeter aperture. Here we have a smaller but more complete set of sieves, starting with the lid at the top. We have the larger sieve placed next and the smaller sieve placed last, which unfortunately isn't 75 micron. It's slightly larger than 75 micron, and whatever passes through this smaller sieve is caught by the bottom pan. So the sieves are placed in order from the lid to the largest sieve and progressively smaller and smaller until the finest material passing through the finest sieve ends up getting caught by the bottom pan. The grading of a coarse-grained soil is an important factor in determining the soil's strength and resistance to settlement. In this container I have a compacted well-graded sand, which as you can see is very dense, almost the consistency of a rock, and a well-graded material when correctly compacted has very great strength in resisting any attempt to deform it. If the soil is well graded, there's a range of particle sizes in contact with all the adjoining particles, and there are no voids for them to move into if there's pressure from above due to building loads or traffic. If we imagine that the soil particles are magnified, if we attempt to distort these particles, the contact between one particle and the other will resist deformation, and if there are particles filling the gaps between the larger ones, then there is actually no room for them to move into, because all the voids are filled and all particles are in contact with each other. So a well-graded material will resist deformation due to this factor. If the soil sample does not contain a wide range of particle sizes, we call that soil sample poorly graded. And if there is a deficiency in particle sizes, there being only a limited range of sizes, then the soil is called poorly graded, gap graded. This material is called gap graded because there are gaps in the soil sizes that should exist between this range, and that range. If on the other hand the material is comprised of particles of only one size, such as one size gravel or all fine beach sand, the material will also be termed poorly graded, but it would be a uniform soil. In other words, a poorly graded uniform soil, either all gravel size or all sand size. Grading is not important for fine grained materials, whether they be silts with symbol M or clays with symbol C, because both silts and clays derive their strength from cohesion. We experience cohesion whenever we wet a silt and find it sticking together and sticking to our hands. In a similar way, if we wet a clay, the dry clay particles become very sticky and very, very slippery. Looking at this representation of a stack of sieves with the British Standard sieve number shown here and the equivalent aperture size in millimetres shown against a selected number, if we commenced with this much material and found that the amount passing each successive sieve was as shown by this type of distribution, we will have an example of a well-graded material. If on the other hand there were deficiencies in some of the grades, so there were some particle sizes missing, this would indicate a gap-graded material. If on the other hand we find that the material was essentially only of one size, with only a small amount larger and smaller, this would indicate essentially a uniform material. One of the areas of confusion in soil classification arises from this inset to table 3.5. According to this inset, in order to have the modifier W or P assigned to the soil, whether it be gravels or sands, the proportion of fines must be less than 5%. If there are more than 12% fines, then the modifier must be either M if the fines are predominantly silts, or C if the fines are predominantly clays. Irrespective of the shape of the grading curve, the modifier must be an M or a C. In the situation when the percentage fine resides between 5 and 12%, then we have what we call a borderline case, and we need to use dual symbols. So GP if it's a gravel poorly graded, dash GM to indicate that we have between 5 and 12% silt. And in the situation where the soil is predominantly sand that has a range of particle sizes and therefore well graded, but has between 5 and 12% clays, then the second part of the dual symbol is SC. The particle size distribution chart shown here is taken from the Australian Standard, and the various soil constituents shown on the top and the sizes of the individual grains shown on the top axis, and intermediate or in between values shown on the bottom axis. The red lines here indicate the boundaries between gravels, sands and fines, and between silts and clays shown by that line there, at the 2 micron cutoff. We can determine the percentage of each soil fraction by projecting along each boundary and then across to the vertical percentage axis, and from that determining how much is in the gravel, sand, silt or clay category. In this sample here, the intersection between gravel and sand is at 80%, which means that there's 20% above that, there being 20% gravel. The intersection here between the fines and the coarse cuts at 3%, so there's 3% fines, and because the fines are all within the silt area, the 3% are all silts. And in between here, in between the gravels and the silts, in this band here, we have the sands. This second sample also has approximately 80% finer than the gravel size, so 20% gravel, but the proportion of fines, in other words the proportion crossing the 75 micron boundary, is approximately 22%. So because we have more than 12% fines, this cannot be classified as W or P. So here we have 22% fines, and the fines are all residing in the silt category or within the silt range of sizes. So we have 22% silt, 20% gravel, and 20 plus 22, 44 taken from 100% gives us 56% between the gravel and the silt size. So the band in the middle here between the gravel and silt, projecting up and then across that band in there, 56% comprises sand. So this second sample would have 20% gravel, 22% silt, and 42 from 100% we said was 58% sand. And there being a range of particle sizes, one would want to classify it as SW, but because there's more than 12% silt, we need to classify it as SM, because the predominant amount is a sand, so it belongs to the sand family, but there being more than 12% silt means that the second symbol has to be an M. Examining this third sample, we have from this intersection here 90 from 100, 10% gravel. From the intersection between sands and silts, we have 40% finer than sand, so we have therefore 10 plus 40, 50, 50 from 100, 50% sand. But beyond this point, we find that the intersection between silt and clay is at the 30% mark, which means that there is really only 10% silt and approximately 30% finer than silt, so there's 30% clay, only 10% silt, so out of the 40% fines, most of the fines are in fact clays. So breaking down these percentages, we have 10% gravel, 50% sand, 40% fines, out of which 30% are clays, 10% are silts, and because we have 60% coarse material, it's still considered to be a coarse grain material, predominantly sand, so it belongs to the sand family, but the modifier now would be a C, because the main constituent of the fines is a clay or are clays rather than silts.